Hello, gentle readers. February 18, 2026. Reading Foundations today. Previous episode was about problem probables, effectively reflecting on the notions about probability theory, that the standard classical account has its limitations, and it's sort of as if after Erdős's giant monster of mathematical independence, about why there's a real atlas of mathematical independence, helping to establish otherwise a variety of what are considered uniqueness results or distinctness results for the laws of large numbers, models of continua Cantor space, limit theorems and probability, and about issues in convergence and emergence in the mathematical functions of completions of the things and the repleteness of the things. So that was a consideration of the usual account of probability theory and statistics, and then about summary and ordering statistics and these sorts of accounts of usual measures of the observable that make for a design of experiment and these sorts of things. Then today is just kind of continuing in this box of books and carrying on forward as about then for matters of if that was about statistical design or the design of statistical experiment, then that's kind of the most recent context and overall this wider context of the considerations of the foundations, that singular term, the subject of study overall. I stopped by a bookstore and was able to find quite a number of salient works. So I imagine we'll look through those a little bit first, and then, as mentioned, to get back into the box of books. These new additions to the library will also be part of the stacks eventually. At some point in time, I should endeavor to make a bibliography of all these works that have been referenced in all these video essays and otherwise the library, to provide what is context, and as for attribution, the usual matter of attribution, meaning to give credit where credit is due, and these sorts of things. There's so many of these concepts of as old wrapped as new, or rediscovered or independently discovered, yet remain as largely part of our canon and dogma in the usual accounts, and for a modern account. So that said, when there are items that I introduce as like these are my fabrications, that term I'd avoid. Fabrication usually means lies, but it also here means as of from the whole cloth and independently. And so when it comes to the ideas are found, then it's usually figured that somebody else has already had these great ideas. It's like they say, great minds think alike, and greater minds think the same. Has that the accounts here of when I introduce something like my own under my own definitions, like the identity dimension, or the hat analysis, or the stop derivative, for examples, or is about heft mechanically, and these sorts of accounts, or the line reals, field reals, signal reals, the models of continuous domains. When I relate those to Xenocrates and Democritus and Archimedes and Aristotle, and Shannon and Nyquist, for example, it's not to make it so that any of these stipulations stand alone for themselves, not be in this weak logicist positivism, but instead that it is a conscious sort of account of this paleoclassical approach, the archaeological of the architectonic, that as well. Hopefully, it will be clear which particular opinions are my own, which I hold and defend, and which one of these are attributed to the canon more widely, matters of attribution and priority, or when multiple sources of attribution arise, is where to give the academic credit. then this accounts here is after, for example, the superclassical and the extraordinary, is that I invented the word for myself, Atlas of Mathematical Independence, because it needs one, the theory. And so now it has one. And so thusly, with these sorts of accounts, then for reading foundations, it's also as of from our literary and deconstructive experience to be understandable, that it's comprehensible, that the relations of these novel or nouveau sorts of accounts are part of a canon and a dogma, and then that's to be considered kind of diligent and conscientious. So, all right, then let's get into these books and see what is being found from them. Well, I stopped by the library the other day. They retired this. It's a novel from John Irving. I've read a bunch of his works, and in his autobiography, the autobiography I have somehow is a signed copy. He's considered a part of American literature in the 20th century and 21st century, I suppose. I haven't read that book yet, but it'll be something to figure out. Let's see here. The Mathematics of Experimental Design, Incomplete Block Designs and Latin Squares, being number 23 of Griffin's Statistical Monographs and Courses. So the Latin squares are familiar to people as Sudoku, or otherwise as the magic squares and Latin squares. They make for that the sums of the rows and columns and sometimes the diagonals are constant. And so given the additive partitions of a number, then how they add up is, according to that, any way you slice it, it appears to be that each slice is the same. Yet no particular cell of this matrix or table or square is the same. So you can generalize that to magic and Latin squares and rectangles and about generalized matrices and generalized matrix products. And the usual idea here about the application of magic squares and Latin squares is that when considering other things that have uniform current, like the flow of liquids or current in electrical charge, has that as well, that it's like any way you slice it, it's uniform, that would be indistinguishable from magic square or Latin square. So when I picked up this book about statistical experiment and design of these things, it'd be interesting to see kind of what they're using to relate that's the properties of the outcome of it being a magic square or Latin square that make it so that from far enough away or from only a particular view, it's indistinguishable from uniform, and as of for the masses and mass terms and aggregates and bulk and flow. So then in this book, let's see here, that this series of monographs is about statistical monographs and courses are as from, this is from the United Kingdom. These other monographs and courses include, for example, multiple time series, multivariate analysis, the fundamentals of statistical reasoning, basic ideas of scientific sampling, characteristic functions, an introduction to infinitely many variates, mathematical methods in the theory of queuing. So queuing theory and network theory kind of go together. Things like Erlang and the study of telephony networks often, but also for traffic networks generally enough. Mathematical methods in the theory of queuing, a course in the geometry of n dimensions, random wavelets, and cybernetic systems. Here there was discussed recently enough the wider wavelets vis-a-vis the denser tensors, and these kinds of things that is to go to show that these are common terms for a long, long time, and they're widely underexplored, that this sort of account of exploration, more of a particular mathematical artifice, is to be considered for what it can intend to entail for transforms, for example, for signal theory, or for models of current and flow, for the usual considerations of motion as about meters per second and seconds per meter. That these are enrichments usually as considered, but also would have direct and particular applicable sorts notions to be developed, to make derived, after definition and derivation to have it so. And then for declaration and definition, for example, in the tractable that computers make for computational advantage, make it so. Geometrical probability, an introduction to symbolic programming, the method of paired comparisons. So this is about the pairwise vis-a-vis the pointwise. And for example, in the computation of summary statistics, the neighbors. And so then trying to figure out, similarly as the geometric perspectives, geometrical probability we might intend to entail. That similarly, these notions of the paired comparisons make for ideas of establishing, for example, the adiabatic or non-adiabatic for systems of inequalities and these kinds of things. Making for the transitive that then a law holds for these things. Statistical assessment of the life characteristic, a bibliographic guide. Now, in many of the studies of epidemiology or otherwise dynamical systems, and the studies of life, the predator-prey relations, logistic relation, and all these sorts of things, there's much to be made of the integro differ and the differ integro, because these tendencies and propensities have feedback. And feedback is a general idea that the output of the system becomes the input of the system. And it's a complementary idea to that when there are implicits in the system, that implicits basically do make for models of feedback. So with the idea of feedback being kind of like after the fact, and for the prior and posterior in these sorts of accounts, here there's always a sort of account that the implicits are functions. For example, is force is a function of time, or these sorts of accounts, making for so that mathematics can have a unified, holistic approach that's thorough. Applications of characteristic functions. Characteristic functions are as the trace, or is kind of as for the scalar and indicators. So the idea of being able to show up with numbers that may provide tests for things like whether a matrix is singular, or for like singular value decomposition or these kinds of things, are examples of when characteristic functions then also have that these as matters of trace and shape and form often then automatically combine themselves to the linear, where their application holds vis-a-vis the analyticity in these sorts of accounts, and where and under what conditions analyticity holds, that being the continuity of things. Elements of linear programming with economic applications. Inequality is on distribution functions. Green's function methods in probability theory. So Green's function is to be considered of a particular development that fit very well in the time and place for then the evaluation of cross product and vectorial products. It's to be determined with relation to that to the Hamiltonian, and as about its usual place in Navier-Stokes and advanced calculus, as it's called. That it's roles under the operator calculus here are generally split out from power law on the one side and convolutional setting on the other side to make for a symmetry that's otherwise lacking. The analysis of variance, or Ronald Elmer Fisher and such. The linear hypothesis, a general theory, econometric techniques and problems. Econometrics is the idea that there's an economy and economics, and it's kind of a qualitative account, and then econometrics is the quantitative account. Stochastically dependent equations, an introductory text for econometricians, patterns and configurations in finite spaces, and then this book, The Mathematics of Experimental Design, Incomplete Block Designs in Latin Squares, by S. Vajda, V-A-J-D-A, doctor in philosophy, Vienna, professor of operational research at the University of Birmingham. 1967. The topics with which the two companion volumes, Patterns and Configurations in Finite Spaces, and The Mathematics of Experimental Design, Incomplete Block Designs in Latin Squares, are concerned have a long history, but the main stimulus to new developments has come from the interests of statisticians in the efficient design of experiments. The origin of some of the patterns can be traced to recreational mathematics or to problems in pure mathematics, particularly number theory. The statistical aspect of most of the subjects mentioned has been dealt with in many excellent textbooks, together with their analysis which leads to inferences about the effectiveness of treatments or other choices, the outcome which is subject to stochastic variation. So the stochastic variation would be along the lines of the overall uniformity of a population vis-a-vis its individuals, for examples. No such analysis is described in the present books, thoroughly described. Here there's a general description of that as kind of what it means. They contain rather the combinatorial aspects of the construction of designs without regard to the practical applications or indeed other usefulness. Patterns and configurations in finite spaces. The first chapter contains the algebra, which is needed in the subsequent pages. This is, of course, not a course in algebra, but only a review of certain parts of it. Chapters 2 and 3 contain the fundamentals of finite geometry, two-dimensional and more-dimensional geometry being treated in separate chapters. Chapter 4, we reach configurations. So the configurations with regards to kind of the characteristics of the things. In the mathematics of experimental design, we start with a short review of algebraic facts and then deal fully with some special cases of configurations treated in the first mentioned book. Thus, balanced and complete block designs are described in Chapter 2 and partially balanced and complete block designs in Chapters 4 and 5, the last chapter being concerned with the special case of designs introduced in the formula, namely those of two associate classes. Chapter 3 is devoted to orthogonal arrays and to a special case of these, namely Latin squares and their orthogonal sets. It contains an account of the most recent results in this field, including the proof of the falsity of a hypothesis by Euler, which was long considered to be plausible. Now here, because conjectures, especially in the long-standing variety, often reach towards that their independence is after various considerations and concerns, we'll have that's kind of let so. It's almost troubling sometimes, especially even in the modern day in the past few years, to see like so-and-so has proved this or so-and-so has disproved this after a long standstill or debates or various conjectures. Because that may have been a bit too early, the closing of that book, that chapter. And indeed, it's often the case that these things have definite counterexamples, in which case they are simply particular application areas, but not having sufficiently determined under what conditions that the configurations would be so valid. They would have their character. The real analytic character to be so. So that said, matters of Ramsey theory and for Birkhoff and the lacunary and stuff like that have a lot of what's going on these days into the quasi-invariant measure theory, which accommodates that it's the super classical with regards to these sorts of the pseudo-differential, for example, accounts of these things. The quasi-invariant measure theory, not to be confused with quasi-modal logic, which is incomplete. These quasi-invariant accounts tend to be more complete because they already include the standard account. Chapter 3, Euler, exercise, matrices, Macnisch's theorem, M-A-C-N-E-I-S-H, Greco-Latin squares, partially balanced, incomplete block designs. So this would be, I'd relate it to flow theory and flow and flux, and the ability to identify that each of these different slices of otherwise uniform cross sections of flow through a square or a round circular pipe would have it be indistinguishable from end to end, whether all these ripples and eddies were just like gradations in these numbers, the magic squares. That it incorporates otherwise the idea of the adiabaticity, not being diabatic, being the non-adiabatic, to be the diabatic, these sorts of accounts. Theory of the Integral by Dr. Stanislaw Sachs, S-A-K-S, second revised edition from Dover Books on Advanced Mathematics. Dover is a wonderful printing house that reprints many books that would otherwise have only a few thousand volumes maybe ever printed, but deserve in their priority for their attribution much, much more to them. I haven't read this, so I wouldn't necessarily comment, but it's by Stanislaus Sachs, second revised edition, English translation by L.C. Young, M.A., with 2 additional notes by Professor Dr. Stefan Banach. So Banach is accounted for in matters of topology and Banach spaces in the functional analysis. And then for equidecomposability with Banach and Tarski about the ability to double a ball by dividing it into variously 4 or 5 points, parts, each everywhere non-measurable, but somehow putting them back together and making equal copies, 2 equal copies, equidecomposability. Here it's accorded that Vitali and Hausdorff already made one of these decades before it came to be that Banach and Tarski kind of made the same sort of thing, because one has an account of the measurability and the other has an account of not being measurable. So the re-Vitali-ization of measure theory is one of these examples of where the priorities and the attribution and even the accreditation of mathematical fact saw various interpretations, and so that the re-Vitali-ization of measure theory is considered a great part of the account of mathematical independence today. Oh, yeah, and it talks about Haar's measure, so Haar, Haar. Haar has a great little sleight of hand to make it so the integral analysis pops up as justified. Now, it would otherwise be on its own account, but then when trying to get it back and forth from differential analysis, there's a great divide and schism because they're kind of opposite sides, opposite corners of a square of opposition. And so then Haar measuring the Haar transform and these kinds of things is its own kind of particular corner of that. So it's an accommodation of sorts. And though it reminds me of L'Hopital's rule and Rodriguez' formula, and that reminds me of Plancherel and Parseval, then it's a little bit more like Plancherel and Parseval than L'Hopital and Rodriguez' formula, which are great accounts of approximations and tests about properties of functions related together by the relations of their derivatives together. And then that Rodriguez's formula is also kind of reminds of Nicomachus's theorem or something like that. Meaning it's like the sum of powers is the power of the sums? Wow. Is that just matter-of-factly a fact of number theory, like casting out nines in number theory? Yeah, these kinds of things. If you've ever happened to find Nicomachus's theorems and these kinds of things. The modern theory of real functions became distinct from classical analysis in the second half of the 19th century as a result of researches, unsystematic at first, which dealt with the foundations of the differential calculus, or which concerned the discovery of functions whose properties appeared to be very strange and unexpected. The distrust with which this new field of investigation was regarded is typified by the attitude of Henri Poincaré, who wrote, Autrefois, quand on inventait une fonction nouvelle, c'était en vue de quelques buts pratiques. Aujourd'hui, on les invente tout exprès pour mettre en défaut les raisonnements de nos pères et on n'en tirera jamais que cela. So, a balance of things, generally. This view was by no means isolated. Charles Hermite, in a letter to T.J. Stieltjes, known for the Hermite polynomials and the Hermitian kind of in matrix methods and analysis, and then for Stieltjes for measure theory, expressed himself in even stronger terms. Je me détourne avec effroi et horreur de cette plaie lamentable des fonctions qui n'ont pas de dérivés. So this is about non-standard functions and these kinds of things, and his horror of the affront of them. Researches dealing with non-analytic functions and with functions violating laws which one hoped were universal regarded it almost as a propagation of anarchy and chaos, where past generations had sought order and harmony. So the entire account of the classical as differentiated from the modern is also kind of in accords with that, about Hilbert's postulate of continuity, since it was given that it would demand an extra axiom to be added in any quarter of set theoretic account of the objects of geometry, and these sorts of things are given to be that then the real laws of continuity, or the matters of the objects of the continuity, have their truths to be discovered as accounts after Zeno, and a deductive account, which is quite thorough for the whole endeavor, actually. Even the first attempts to establish a positive theory were rather skeptically received. It was feared that an excessively pedantic exactitude in formulating hypotheses would spoil the elegance of classical methods, and that discussions of details would end by obscuring the main ideas of analysis. It is true that the first researches hardly went beyond the traditional formal apparatus fixed by Cauchy and Riemann, which was difficult to adapt to the requirements of the new problems. See, I'd kind of point to Maclaren and Weierstrass for that. Nevertheless, these researches succeeded in opening the way to applications of the theory of sets to analysis, and to quote Henri Lebesque's inaugural lecture at the Collège de France, the great authority of Camille Jordan gave to the new school a valuable encouragement which amply compensated the few reproofs it had to suffer. Baire, Borel, and Lebesque, these are the names which represent the theory of real functions, not merely as an object of researches, but also as a method, names which at the same time recall the leading ideas of the theory. So functions and functional analysis is noted here. It has that functions and topology are the most fluid of definitions of the objects of mathematics over time. And so then the theory of real functions with regards to the continuous and the differentiable also has that they're non-standard functions. Everybody's first and most famous non-standard function, Dirac's unit impulse function, the Dirac delta, used to justify Fourier style analysis, which is ubiquitous, and otherwise ubiquitous, the Dirac delta. Anywhere that a sort of account of a non-standard function exists at all with real analytical character, then the natural unit equivalency function is perhaps the most central and primary of non-standard, not a real functions, yet with real analytical character, that thus provide kind of the envelope, the context, and the surrounds of the theory of real functions as it's purported to be. Excellent accounts of this subject can be found in the treatises de la Vallée, Poisson, Fonctions d'ensemble, Intégrale de Lebesque, Classe de Baire, Hausdorff set theory, Mengenlehr, Hahn, Theory des Reellen Function, Kuratowski, third volume of the present collection, and finally in the book of Sierpinski, Topologia Ogólna in Polish, and its English translation, General Topology, to be published in 1934 by the Toronto University Press. The other line of researches, which arises directly from the study of the foundations of the integral calculus, is still more intimately connected with the great trains of thought of analysis in the last century. So that's almost indubitably Poincaré and the Cedos analysis. And then for algebraic geometry, Lefschetz and Picard and so on. On several occasions, attempts were made to generalize the old process of integration of Cauchy and Riemann, but it was Lebesque who first made real progress in this matter. He just kind of turned it on its side. And this Stiltes is like, well, either way you look at it. And then we have the meromorphic and free analysis these days. But the account of like the identity dimension and these sorts of things is like its original analysis. Its original is about the origin vis-a-vis the coordinate analysis. At the same time, Lebesque's merit is not only to have created a new and more general notion of integral, nor even to have established its intimate connection with the theory of measure. The value of his work consists primarily in his theory of derivation, which is parallel to that of integration. This enabled his discovery to find many applications to the new, most widely different branches of analysis. From the point of view of method, and made it possible to reunite the two fundamental conceptions of integral, namely that of definite integral and that of primitive, which appeared to be forever separated as soon as integration went outside the domain of continuous functions. That's quite a number of different things. And then what it reflects on besides the derivative and antiderivative, and the integral and anti-integral, I guess one might say, and the notion for functional analysis, that there's an operator calculus about those, which is a great sort of account, as was mentioned as for the ordinary differential equations and the extraordinary differential equations, that the usual meaning of that. Then as well about the continuity and discontinuity of the functions is a lot about the topology. And what is a continuous topology, which normally goes without a definition in the linear curriculum. yet is exactly what is intended to be upheld, all the theorems that make then the laws of arithmetic arrive. So for measure, and then that measure is pretty much given as like there exists a sigma algebra of these point sets, so you can add them up, and their character and their sum is their sum character. That the sum of the character is the character of their sum. That's all the measure theory's fundamental statement is measure, and then measure 1.0, that it relates to a unit. The theory of Lebesgue constitutes the subject of the present volume. So while distinguishing it from that of Baire, we have Baire, we have no wish to erect an artificial barrier between two streams of thought which naturally intermingle. Well, yes and no, because intentionality and extensionality do and don't hold without and with loss of generality. That the generality and abstraction are complementary themselves. On the contrary, we shall have frequent occasion, particularly in the last chapters of this book, to show explicitly how Lebesgue's theory comes to be bound up not only with the results, but also with the very methods of the theory of Baire. Is not the idea of Denjoy integration at bottom merely a striking adaptation of the idea which guided Baire? Maybe not. I have forgotten Denjoy, D-E-N-J-O-Y, as a name, but I'm reminding of its description. Kind of like the difference between the complex plane and the Wessel's plane and the Argand plane, which so many people say, oh, there's just no different. That's just a diagram of C on R squared. But they were different, and their intents are different, and the derivations following them are different, and they have different expectations eventually of analyticity. So Denjoy and Lebesgue and Baire are not necessarily the same, any more so than we'd say necessarily that Newton and Leibniz and their methods of the derivative and the integral are the same, because they're not. The differential analysis and the integral analysis have two quite thoroughly different approaches. Then for how they come together, and the different integral and the integral are different. Denjoy constructed a transfinite hierarchy of methods of integration, starting with that of Lebesgue, whose successive stages are connected by two operations, one corresponding exactly to the generalized integral of Cauchy, and the other to the generalized integral of Harnack-Jordan, H-A-R-N-A-C-K, Harnack-Jordan. So this is good to know that there are these multiple accounts of integrals, because there's multiple accounts of measure. And sometimes you'll see, for example, today they'll say, oh, remember Jordan measure? So it's like you can add up segments in a line, and it adds up to the line that segments. Well, that's now called Jordan content. Well, why would that be? It's like, oh, because then you'd have non-standard functions existing in this theory, and with real analytical character. And that would make a lot of simple accounts of the linear narrative, of the linear curriculum, this simple standard account, quite thoroughly more involved to keep from tripping over themselves all the time and contradicting each other. It still is what it is, though, so it is what it is. So this introduction by Sachs is appreciated from Warschau, May 1933. I don't speak Polish or have much experience with it. Czartiorski Kalki. Warschau, 1930. Wydawnictwo Mianowskiego. Instytutu Papriona Nauki. In this preface, I made no attempt to write a history of the early days of the theory, but still less to settle questions of priority of discovery. But since an English edition of this book is appearing now, I think I ought to mention the name of W.H. Young, whose work on the theory of integration started at the same period as that of Lebesgue. So then chapter 1 is the integral in an abstract space. Chapter 2 is Carathéodory measure, C-A-R-A-T-H-E-O-D-O-R-Y, Carathéodory. And that's about, it looks like it's to be about the sigma algebras. Functions of bounded variation, the Lebesgue-Stieltjes integral. Derivation of additive functions of a set and of an interval. Area of a surface. Major and minor functions. Area of a surface gets involved like the spiral space filling curve. that being the natural primitive of such a thing, the areal. And then, but he mentions the Burkill integral, Burkill, and Rado and Tonelli, Rado's theorem and Tonelli's theorem. Integrals are the expressions of de Gioschi, a name, de of Gioschi, Geo umlaut CZE. A theorem of Lucin, definitions of Denjoy-Lucin, of generalized bounded varieties or variation. Denjoy integrals, a theorem of Hake, Alexandrov, and Luhmann, Hake, Hake, or Hake, Alexandrov, and Luhmann, Looman, Luhmann. Derivatives of functions of one or two real variables. A theorem of Denjoy-Khinchin, Khintchine. Three theorems of Banach. And then note 1 by Banach is on Haar's measure, and 2 is the Lebesgue integral in abstract spaces. So that would generally be considered to be a diagram and not necessarily so connected to its components for matters of analyticity, which would need hold for real analytical character. In terms of algebraic geometry, and so on. So descriptively, this, for me, it helps me kind of fill out my categorizations of the usual accounts of the integral is after the Riemann integral, the Lebesgue integral, and then the Stieltjes integral, and then the meromorphic functions is precedingly more general. A source book in mathematics. David Eugene Smith has 125 selections from the classic writings of Pascal, Leibniz. I always say Leibniz, and you'll mostly hear Leibniz. Euler. I would often say Euler, but I'm told often the first thing in class whenever anybody thinks they're introducing Euler, they'll say its name is, it's not pronounced Euler. It's like, well, Euler, it kind of is. Fermat, Gauss, Descartes, Newton, Riemann, usually Riemann, and many others. Starts with a picture of Newton. Not really a usual picture of Newton. It looks like he hasn't been skipping a few meals, The author's preface. The purpose of a source book is to supply teachers and students with a selection of excerpts from the works of the makers of the subject considered. Talks about the fields, some acknowledgments. Robert Record, R-A-C-O-R-D-E, Stevens, Simon Steven, known for fractions, also for the p-adic numbers, which are as made for accounts of products of infinite numbers, or what it would be like if objects that had otherwise consequences of there being arithmetical were unbounded, and yet they had two ends of them instead of just one end, like numbers do it normally from their least significant to the most significant in these sorts of accounts. That from the little end or the big end are they both significant? Simon Steven. Dedekind on irrational numbers. Now Dedekind, I kind of just see as a hanger-on and an aggrandizer, because he's like, Dedekind completeness is completeness, and that's our real Archimedean field. And it's like, you mean it's Archimedean, and it's in real. And it's like, well, then my Dedekind cuts are just subsets of rationals after cassette theory is new, and I made that. It's like, well, it either is or isn't members of the complete ordered field already. And if it is, then those are including real numbers. And if it isn't, then they don't exist there to make that to be like so. So much like ordinal assignment for cardinals erases the difference between cardinals and ordinals. Dedekind cuts are just kind of a useless convenience, because otherwise we'd say, and when I say we, I mean the linear curriculum would say real numbers, according to descriptive set theory, are equivalence classes of sequences that are Cauchy, not that they are Dedekind cuts. Those are two different things. So, and then the classical account of the Pythagorean is almost all rational, but it admits there are irrationals. Has that then the Cantorian account of the transcendental, almost all transcendental, yet there are rationals. Has it either way. The other one is big, and then for things like Vitali and making it measurable again and stuff like that, there is a row in the middle, the re-Vitali-ized, in this sense. John Wallis on imaginary numbers. Wallis is known for many identities that says, oh, you want infinity? Here's a series that gives it. Here's another one. Here's another one. Here's another one. These kinds of things. Wessel on complex numbers. Pascal on the arithmetic triangle. Bombelli and Cataldi on continued fractions. Bernoulli on Bernoulli numbers. Euler on every integer as a sum of 4 squares. Euler on the use of E, Euler's number, to represent 2.718. Hermite on the transcendence of E. Gauss on the congruence of numbers. Gauss on the third proof of the law of quadratic reciprocity. Quadratic reciprocity is really cool. And then it's also kind of like, as we were talking, or as was mentioned, Plancherel and Parseval, it's also kind of like the other account of why quadratic reciprocity is a bridge result of these kinds of things for like the Haar measure and Haar's analyticity in the convolutional setting. Kummer on ideal numbers. Chebyshev on the totality of primes. See, that's a conjecture, because there are models of the integers where infinity is, or surrounding infinity, are primes or composites. They're different ones. Napier on the table of logarithms. Delamain on the slide rule, Outred on the slide rule, Pascal on his calculating machine, Leibniz on his calculating machine, Napier on the Napier rods, or slide rule, Galileo Galilei on the proportional or sector compasses, Durkheim on nomography, Cardan on imaginary roots. So that's interesting that Cardan, long before Cartan, has things going on with imaginary roots. Cardan, Ferrari Cardan, Fermat, John Wallis, Wallis and Newton, Leibniz and the Bernoullis, Horner on numerical higher equations, Roll on the location of roots, Abel on the quintic equation, Leibniz on determinants, Bernoulli's verses on infinite series, Bernoulli on the theory of combinations, Galois on groups and equations, Abel's theorem on the continuity of functions defined by power series, Gauss on the fundamental theorem of algebra, and a bunch more notable and important works. So this is a great sort of account of work. It's like not only did they reprint a book, it's also a source book. Might not be like the sole source, but it kind of is. Here then, these are a couple of other different works I kind of had kind of stacked together. So when I found at this store was Einstein, the Principle of Relativity, and so this is 20 years after the Annus Mirabilis, and this was reprinted in the 60s. So it's current, kind of as of then. And it's got Lorentz, Weil, Minkowski, and Einstein, each having written sections in this. And this is pretty good. And then what I had taken from it so far is that the article from Einstein on electrodynamics has that it's kind of the opposite account of the electron and photon, because it's like for the photovoltaic and the account that made for the Planckian and it kind of made for E equals mc squared for special relativity from 1905. That's kind of like the inside, and then the outside he's like, no, considering this from the outside, let's start all over so I can have it both ways. And so it makes for another account of like, well, somebody like validated Einstein again, and it's like, which way, you know, because they otherwise they're pointing in opposite directions and don't agree. They don't have to agree. They're pointing in opposite directions, but they're not consistent together in the same sort of sense because of definitions. That's what that's what I got from reading Einstein's Out of My Later Years, that being his last and final word on the matter and what he considered that would be defensible forever, because he won't be made a fool as much as possible. And then these other accounts kind of are what can be read from his words. So that said, that the Einstein's Out of My Later Years, the theory of relativity, is very careful and quite good, and it doesn't need to say much, and it does it in a very good way. On the Influence of Gravitation on the Propagation of Light, by A. Einstein, page 97. Translated from Über den Einfluss der Schwerkraft auf die Ausbreitung des Lichts, Annalen der Physik, 35, 1911. In a memoir published 4 years ago, I tried to answer the question whether the propagation of light is influenced by gravitation. I returned to this theme because my previous presentation of the subject does not satisfy me, and for a strong reason, because I now see that one of the most important consequences of my former treatment is capable of being tested experimentally. For it follows that the theory from here to be brought forward that rays of light passing close to the sun are reflected by its gravitational field, so the angular distance between the sun and a fixed star appearing near it is apparently increased by nearly a second apart. In the course of these reflections, further results are yielded which relate to gravitation, but as the exposition of the entire group of considerations would be rather difficult to follow, only a few quite elementary reflections will be given in the following pages, from which the reader will readily be able to inform himself as to the suppositions of the theory and its line of thought. The relations here deduced, even if the theoretical foundation is sound, are valid only to a first approximation. So gently, carefully, Einstein points out that the great success of the predictions of relativity is about optical lensing, or about gravitational lensing, are better than what there was before, but not perfect. And secondly, he gives an account that there's other stuff. Then when he says reflections and then reflections, it reminds me of Einstein's use of different terms for spatial and spatial, for general relativity and special relativity, respectively, because that way he's just kind of deftly introduced the notions that, if you erase the difference, then you can forget the difference. There's no difference. But at the same time, he does mean that. And then it goes saying that there are different implicits in the formulas so represented, making for accounts of feedback that would vary. So he's not ignorant when he's being careful in the sense of that being careful in the sense of not being wrong and not giving people contradictory alternatives to hurt themselves with, but at the same time careful in the sense of that given a correct sort of reading, it is there already. He's like, oh, I've had priority for that ever since forever. You just didn't notice. Hypothesis as to the physical nature of the gravitational fields. This would be useful to read some more because it helps reflect some of his broader thinking on these sorts of matters. He gives a usual account of the Laplacian, except instead of all three components being zero, he just makes the z-squared component be negative gamma. So it's not a Laplacian, because the Laplacian would have those be zero. But he just says that negative gamma is this other term, so whether that's uniform acceleration. So then uniform acceleration gets into all the higher orders of acceleration. Then for the first order, then, that's just a constant. But we arrive at a very satisfactory interpretation of this law of experience if we assume that the systems K and K prime are physically exactly equivalent. That is, if we assume that we may just as well regard the system K as being in a space free from gravitational fields, then we regard K as uniformly accelerated. So the weak and strong gravitational equivalence principle is another sort of account about these. The circular here, it's generally considered to start. And it is for Einstein, too, with Einstein's bridge and the radially and axially symmetric. So this is a good book, and it has other papers from Einstein and Weil. Let's see, what is Weil talking about here? Gravitation and electricity. basically is he just writes it in integrals, and it's like obviously it must be these integrals. Matters of curvature. So while in his accounts, Einstein's Sommerfeld. Notes by A. Sommerfeld. The following notes are given in an appendix so as to interfere in no way with Minkowski's text. They are by no means essential, having no other purpose than that of removing certain small formal mathematical difficulties which might hinder the comprehension of Minkowski's great thoughts. So a reductionism, I'd kind of guess, but yeah, he just gives a small angle approximation. It kind of looks like, and as after the quadratic, then the terms after the first order approximation, as Einstein carefully notes, is not saying anything. So then it's just it's struck from the derivation, because otherwise it would be a lot more. It would always have a symbol present. So these implicit symbols, yet always exists. Minkowski, Einstein, Lorentz. So there's more to be read from this. Then this is just a copy of Boyer's A History of Mathematics. And so you can see that the history of mathematics is quite a bit thicker than a Principle of Relativity. Einstein's Clocks, Poincaré's Maps, Empires of Time, by Peter Galison, Galison. So I started leafing through this, and this is pretty good reading, because it's kind of a historical account. Because Poincaré was around for a couple decades before Einstein, and Poincaré was a giant and a geometer, and Poincaré completion is kind of one of the most usual accounts of repleteness and for the continuous manifolds and a complete reticulation vis-a-vis the Euclids and a smooth plane. So Poincaré is kind of related for the analysis cetus, which is kind of an original analysis. For geometry in an analytical setting, then Euclid, of course, is known for Euclidean geometry and plane geometry, but mostly for points and lines, their theorems. So, and figures more generally, the affine, the conformal, and the affine. So this book is sort of a historical account, but I've been looking for some of the concepts that it might get related into pointing to particulars of who have the things. So the acknowledgments the author reads. I have benefited enormously from discussions with many students and colleagues. It is a privilege to be able to particularly to thank many people. Over the years, it's been a pleasure to have learned as well from many discussions with Einstein scholars, these people, and help of research assistants and his editor, many archivists, especially at the Observatoire de Paris, the Archives Nationales, the Archives de la Ville de Paris, the New York Public Library, the U.S. National Archives, the National Archives of Canada, the Burger Bibliothèque Bern, and the Staatsarchiv Bern. So clocks and Einstein's clocks and Poincaré's maps has that there's the energy and the intelligence, and then there's so many people have taken Einstein's clocks and saying, well, he made time relative, meaning it's not fixed anymore. It's like, well, Einstein definitely had a clock hypothesis in his theories, but the relativity part is just sort of a tractable analytical side. Not to be confused with the acausal or asynchronous. Douglas G. Greenwood's Manual of Electromechanical Devices. Component types, characteristics, design applications. So this is a bit more from the engineering, and it's quite outdated. A typical compound wound sleeve bearing DC motor generator. So for things like AC and DC motors and generators, clutches and magnetic clutches, for solenoids, one of mentions, a Scherbius machine. Wound rotor slip control, Scherbius, Scherbius. Speed setting, variable voltage transformer, So variacs and notions like that. Here, there's still the notion and the idea of the thyrototron to complement the thyrotron as not a solid state device, but a plasma device. So that essentially is a solid state device. It's got no moving parts except the field, but it makes rotatory motion out of an electrical circuit without actually having any mechanically rotating components, the thyrototron. It essentially is a consequence of Faraday rotation. So naturally, from Faraday law, an integral formula for electrical current. Verniers, spring returns, cams, switches, controls, potentiometers, controls, the author was currently associate editor of product engineering, where he was responsible for the magazine's coverage of mechanical designs and technical reference data. The author was a member of the ASME and a senior member of the IEEE. Hunter Rouse, Elementary Mechanics of Fluids, a Dover reprint. Now, so the other day, there is read here from Ruth's about mechanics of flow and mechanics and kinematics, and so their motions and the flow of them. It's about the kinematics as that momentum is only conserved in the open. That momentum is not a conserved quantity, energy is a conserved quantity. And inertial bodies are the subjects of discussion in the theory of relativity, according to Einstein. So momentum then is fungible because it relates really well to models of force, and what do I add in to get what to add out. But matters of torque and the static and so on are well known to have empirical effects outside. So that's Ruth, R-U-T-H. So this is Rouse, Hunter Rouse, Elementary Mechanics of Fluids. So let's make an elementary account. Then I'll be curious as to whether this is more of a linear account and for fundamental accounts, or if it's more of a potentialistic an account. Mechanics of fluids is evidently not merely traditional hydraulics under another name, or even a combination of hydraulics with certain aspects of aerodynamics. Rather, it's fundamental treatment of fluid behavior as the mechanics of solids is of the behavior of rigid and elastic bodies. In the effort to provide a textbook for an elementary mechanics course in fluid motion, the author assembled in 1940, so 80-some years after Ruth there, a preliminary series of notes for undergraduate study at the University of Iowa. After 2 years of use, the notes were considerably revised, and during the following years, for the revisions and additions made in preparation for publication in book form. The present volume, therefore, represents the third edition. The original notes, the major portion which reflects experience gained through 5 years of teaching by various members of the mechanics staff. The word elementary appearing in the title has been used advisedly since the subject matter presumes no previous training in flow principles, in fact, no prior knowledge of mechanics. Beyond that, taught in engineering physics. The book does not, however, represent an oversimplification of what is at best a complex subject. Saying that it uses calculus. I don't know if that still intends to entail that it's thing. So at least it has hydrodynamics and hydrostatics. That's the usual distinction. Kind of like integral and differential are quite a usual distinction, and there are whole fields that know nothing of the other side. Then it's similar with hydrostatics and hydrodynamics, but that usually gets more involved in the practical because you're always going to have a pool or a reservoir besides a jet. So they both are usually quite involved. One imagines. One-dimensional method affects the viscosity, so the viscoelastic almost always involves terms of continuity, and then as Sedow puts it, for the gyroscopic. So for a mechanical reduction of the things. But then getting on all the kinds of stuff like waves and layered media and all that kind of stuff, or reflections, as Einstein might put it, with regards to reflections and connections. These are the kinds of things. Well then, gentle readers, that's about an hour. Sort of a long-winded utterance. I'm not sure if that's even more than one sentence. But it is. It's to be considered when transcribing such a thing, basically that to demarcate a complete, well-formed grammatical sentence anywhere possible, that as long as they all are such that it's a correct enough sort of reading. Well, then I'll wish you a good day and fare thee well. Until next time. Reading Foundations. Reading is fundamental.